Problem number 5, it says an electron is accelerated by a uniform electric field of 1,000 volts per meter. Pointing vertically upward, use Newton's laws to find its velocity after it moves 0.10 centimeters from rest. Then find the speed used in energy methods. And lastly, does the electron gain or lose potential energy? Oh man, that's a lot of work. Why did I send that for homework? So let's try it out and see. So for problem number 15, we need to kind of think this through. An electron will be accelerated downward because it is negatively charged. So maybe I should draw a picture. So let's read this one more time. It says electron is accelerated by a uniform electric charge pointing, or electric field pointing vertically upward. So an electron is accelerated by an electric field pointing upward. Find its velocity. Okay. So there's going to be an acceleration, and we can kind of think of this in terms of gravity. I think that's what they want us to do, is try to relate this. So remember that force is equal to mass times the acceleration, okay? And that if I rearrange that, then I get the acceleration is equal to the force over the mass of the object. Well, we also know that acceleration can be equal to the point charge times the magnitude of the electric field all over the mass of the object. Also, because the first part of the question says let's use Newton's laws. So that means we're going to use kinematic laws. And so we're being asked to find a velocity, and it starts from rest. And I think I'm going to plug in this acceleration. So the one kinematic equation I'm going to try is this one. The final velocity is equal to the initial velocity squared plus 2 times the acceleration times x. And I guess you could think of that as delta x, or the displacement. But here's the thing, the initial velocity is 0, so that kind of goes away. So really what you have is you have the velocity, the final velocity squared is equal to 2 times the acceleration times x. And so let's list some of the things that we know. We know that x was equal to 0.10 centimeters, which should translate to 0.001 meters, right? Let's list some other stuff too. It was an electron, so then the charge Q. Actually, I'm going to write this down underneath so I have a little more room, so it's not so cluttered. So now, what I want to do is I want to solve this. Actually, I want to solve for v. So I take the square root of both sides, and I get the final velocity is equal to 2 times the acceleration times x. Okay. Well, we said that the acceleration is equal to this, so we're really going to take the square root of 2 times q e over the mass times the displacement x. Okay. All right. So now I got to plug some numbers in. So now over here, it's an electron. So the charge of an electron is 1.6 times 10 to the negative 19 coulombs. And we're talking about a point charge. And then the mass of an electron is very small, so it's 9.11 times 10 to the negative 31 kilograms, very light. We said that the displacement was 0.0010 meters, and the electric field was given to us, which was, what was that number? 1,000 volts per meter. Okay. You notice that they changed the units to volts per meter because we're going to have some cancellations with the meters and stuff. So we're going to have some dimensional analysis and some things to take care of itself. So really, the Newton's law is this thing here. So this is when they ask us to do Newton's law. This is what they're asking us to do. But we are using some properties of electrical fields to help us find that acceleration. So now let's plug and chug. So the velocity of this is the square root of 2 times the charge of an electron times the electric field times 0.0010 meters. I had to squeeze that in there. All over the mass. And we got to take the square root of that. And if you plug that in your calculator, you should get 5.9 times 10 to the 5th meters per second. And that would be going down, right? And so, oh, I forgot to draw the picture. So remember that we have an electric field. And so for an electric field to be pointing vertically upward, remember that the field goes away from the positively charged plate, or however, this could be one scenario. Based on, let's read the question again. So it says an electron is accelerated by a uniform electric field pointed vertically upward. Use Newton's law to find the velocity after it moves 0.10 centimeters per rest. So we can assume that this electron that has a negative charge is going to be attracted to the positive charge, and it'll be accelerated from this position downward. 0.0010 meters from rest, and the velocity it'll be at after that takes place is going to be this right here. So that's what we're trying to figure out. Okay? You might say that's counterintuitive because everything I taught you, we were talking about positive charges. And so normally if I had a positive charge in here, normally the positive charge would repel, and that would want to go this way, but that isn't the case. So the electrons will usually oppose the electric field, but we use the magnitude of the electric field to help make our calculations. So that was just part 1 of this problem. Part 2 of this problem said, now find the speed using energy methods. Okay, so now this one might be a little easier. Oops, oh, I totally deleted that. So now for the energy methods, what we're going to do is we're going to do the same thing, except now we got to remember that the electron will accelerate down. And so remember that the work energy theorem states that the absolute value of the work, because this we don't care about the going down, up or down, is equal to the charge times the electric potential difference, and then based on that, we can say that this is equal to this delta x. And then remember that's also equal to, remember the work is also equal to the change in kinetic energy. This is the part that we're interested in, this right here, which is the final kinetic energy minus the initial kinetic energy. We know that the initial kinetic energy is 0. Theta is 0. So the initial kinetic energy is 0 because 1/2 times the mass times the velocity squared. The velocity is 0, so this whole thing is 0. So that's just equal to the final kinetic energy, which is equal to 1/2 times the mass times the final velocity squared. Whew, that was a lot of work. So now, working backwards from that, I can say that this right here is equal to 1/2 times the mass times the final velocity squared. Okay, multiply both sides by 2, and I get 2 times the charge of an electron. That's what the C stands for. That's the charge of an electron. Times the electric field magnitude times the displacement is equal to m times the final velocity squared, divide both sides by m, and then take the square root of both sides. And so then I guess I get velocity, the final velocity is equal to the square root of 2 times the charge of an electron times the electric field times the displacement all over the mass of the electron. Alright. Oh, did I write the wrong thing down here? No, that's right. Okay. So now, same thing. The charge of an electron is just going to be 1.6 times 10 to the 19. Now you might ask, why'd you write it down this way, Mr. Adams? Because the charge is the charge of an electron, and the difference is equal to the electric field times the displacement, right? Or ED, we could say it that way too. You probably saw this in your notes. ED equals ED. It's the same thing. So now we got all of our variables, and we just need to list the numbers for that. So the charge of the electron is 1.6 times 10 to the negative 19 coulombs. The electric field, capital E, was 1,000 volts per meter. The displacement, delta X, is 0.0010 meters. And then lastly, the mass of an electron is 9.11 times 10 to the negative 31 kilograms. Whew. All right, so let's plug all that in. The final velocity then of this is equal to 2e, whoops, I got to put the numbers in now. 2 times 1.6 times 10 to the negative 19 coulombs, that's that, times the electric field, which is 1,000 volts per meter, times the displacement, which is 0.0010 meters, all over the mass of the electron, which is 9.11 times 10 to the negative 31. If you, guess what, if you plug that in your calculator, and I think that's pretty, this is the cool thing, it's 5.9 times 10 to the 5 meters per second, and that's, again, going down. So then it says, the last part of the question was, lastly, so the good thing is that this question, this part right here, using Newton's law, was equal to this thing, so that's a great way to double check things. But lastly, it says, does the electron gain or lose potential energy? And so here's where it gets a little interesting. So basically, since the electric field does work, the electron does lose potential energy. So it actually does lose potential energy. And the reasoning for that is the field does work. Okay?